Hi, thank you for checking out my talk. I'm Ryuji, and here I'll be briefly talking about our recent work on one-shot yield cost relation in general research theories. This is a joint work with Bartosz Regula and Mark Wilde, and our manuscript is going to be on archive very soon. So this work is on the fundamental relation between the distillable resource and the resource cost. So this topic was intensely studied in the setting of entanglement, where in the asymptotic limit, people figured out that the distillable entanglement cost have such a relations, where the distillable entanglement is upper bounded by the entanglement cost. So this also makes sense operationally, because otherwise one could generate the infinite amount of entanglement only using the LOCC. However, this problem becomes a bit more subtle when you consider some one-shot or non-asymptotic regime, which might also involve some non-zero errors there. And if you define the one-shot entanglement yield and the one-shot entanglement cost like that, and recently the Mark Wilde presented the fundamental one-shot relation between the entanglement yield and cost, which also involves the error factor, epsilon 1 and epsilon 2. Then this epsilon prime is a function of epsilon 1 and epsilon 2. So, but now one can ask, because entanglement is not the unique, important quantum features, so can we extend this relation to more generally? Is this a unique, relation to the entanglement? So we answer this question at a very high level of generality, where we extend the yield cost relation to general research theories and also channel transformations. So general research theories refers to the framework that includes not only the entanglement, but also the arbitrary type of quantum resource, which involves, for instance, like quantum coherence or quantum thermodynamics. And the channel manipulation, we are interested in even the manipulating the quantum channels using the super channels. But also note that this state transformation is a special case of channel transformations. So our general results are readily applicable to the state transformation case as well. And we do that at the quite high level of generality using this framework introduced here, which also takes into account some specific structures that theories might have, for instance, the Bell-known locality or measurement incompatibilities. Then we can now define the one-shot resource yield and one-shot resource cost for some given noisy channel E and some given reference target channel T. So we can now state the general one-shot yield cost relation that's applicable to the general research theories of quantum channels in this way. But one might be also interested in how our one-shot relation could be connected to the asymptotic limit in a smooth way. So in the asymptotic limit, we can even say state the strong converse inequality that involves a strong converse rate, which is an optimal rate with which the error does not approach 1. So we can get the following inequalities that has a strong converse rate in either side of these inequalities. So, but in particular, again, for some conditions, but particular, if you are interested in also the state transformation only, then for some additional conditions, you can identify this, the distillable resource with the strong converse rate of the distillable resource. Then you will get some double-sided strong converse inequalities here. But we know that these above results hold under some condition in terms of the resource evaluation of some target channel T. So these are two resource channels we consider in the manuscript. So this, in other words, the evaluation of these resource measures for this target channel T plays a major role in our discussions. So this motivates us to consider the evaluation of resourcefulness of some class of input resource. So is there any nice operational means to compute resource measures? So this might have a separate interest, but it's also related to this, yield cost relation there. This is inspired by the entanglement theory, where you have the LOCC twirling operation like this. Then this maps the state to any state to the Bell state or its complement. Then this enabled us actually to compute the resource measures for the isotropic states, class of isotropic states. So we can, use this insight and extend it to general research theories, where we introduce a twirling-like operation, free operation in general research theories, and we can actually use that to exactly evaluate some resource measures for the generalized isotropic state. So these smooth resource measures include the hypothesis testing measure, the max relative entropy measure that generally involves a quite, complicated optimizations, but now we can get exact analytic evaluations using this trick. Then we indeed apply that to the research theory of magic and get some non-trivial evaluations of the magicness of some resource states. So we also discussed some technical contributions that might be also useful in other settings in the manuscript. So the manuscript should be up quite soon, so please take a look if you're interested. With that, I thank you for your attention.